I'm Patty Simpson with Simpson Math. In this video, we're going to find the end behavior of our polynomials. So in a previous video, we noticed some patterns about the polynomials. We noticed that when their leading coefficient, that number that was out front of the polynomial, when that's positive, then the graph is going to rise on the right. But if our leading coefficient is negative, then it's going to fall on the right. Then we also notice that when our degree of our polynomial is even, we have same end behavior. But when the degree of the polynomial, that highest degree on our polynomial, when it is odd, we have opposite end behavior. We also saw that when that degree of the polynomial, the highest degree on our polynomial, if we take that and subtract 1, it shows us the number of terms we expect within our graph. And that degree of our polynomial also tells us the number of linear factors or the number of roots that we expect in our polynomial. So let's go through and practice finding each one of those just by looking at this polynomial. First of all, we know it's a polynomial because the exponents are all non-negative integers. So let's go through and just talk about what's happening on each side. Well, the first thing we're going to look at is the leading coefficient. So we're going to first find our leading coefficient. The highest degree here is 4, so the leading coefficient is a -5. Notice that -5, what do we care about that? What helps us to determine what's happening on the right? Well, what we care about is whether it's positive or negative. So I'm going to tell my reader that it is a negative leading coefficient. And because it is negative, that tells me that it's going to fall on the right. So my students know that when they are explaining what's happening on the right, that what's important is that my leading coefficient of -5 is negative. And that's what's important, is this negativity tells me that it falls right. Then I can find out what's happening on the left by looking at the degree of the polynomial. So in this case, the degree of the polynomial is 4. So I'm going to write that down to let my reader know my degree of my polynomial is 4. What do I care about that 4? How do I know what's happening on the right if my degree is 4? Well, I look to see, is that degree even or odd? In this case, my degree is even. So I need to, again, let my reader know that this is even. And because it's even, we're going to have same end behavior. And that same end behavior means that if it's falling on the right, it's also going to be falling on the left. So it falls left. For my students, we need to make sure that we include these things, that the leading coefficient is negative, so it's falling right. And then the 4, what we care about that is it's even, and that evenness causes it to be the same on the left, so that it falls left. Then our degree of our polynomial, -1, so these last two, I know that the degree of my polynomial is 4, and that 4 minus 1 gives me 3, which is the number of expected terms. So I have 3 expected terms. And then the last thing it tells me is that because my degree is 4, I expect 4 roots, or there will be 4 roots in this particular polynomial. Now I can give a sketch of this just based upon that information. I know that it's going to fall to the right. I know that it's going to fall on the left. I expect 3 turns. So here's 1 turn, 2 turns, 3 turns. 1, 2, 3. Now that may not be exactly what it looks like, but there's my expectation is that it's going to look something like that. Let's just practice for a minute some things that we've learned before about polynomials or just about functions in general. So for instance, in the past, we have done this, where we have our function and we insert 0 for x. That just says that we're going to find our y value when x is 0. Let's do that now. If I were to put 0 in everywhere I see x, I'm just going to input my 0 everywhere I see x. So in place of x, I'm now just going to put 0. And I'm going to find out what my y value is when my x value is 0. Well, 0 to the 4th power is 0. 0 to the 3rd power is 0. And 0 squared is 0. So 0 times each of those is 0. So I just end up with 0. There's going to be a point on this function at 0, 0. So we have just found a point on our graph where our x value is 0. All right, let's look at some other examples here. There's one example. Let's do another and see if we can find the end behavior and maybe give a sketch of that function. So here's another function where we have 6x cubed plus 5x to the negative 2 plus 4. And the first thing we do is we look at that function and we notice it has a negative exponent. This is not a polynomial. We don't need to worry about the end behavior of that one because this is not a polynomial. Remember that polynomials have to have non-negative integer exponents. Let's look at another. We have f of x is equal to 6x to the 4th plus 3x to the 1/3 power minus 3x squared plus 2. Again, this one is not a polynomial because it does not have non-negative integer exponents. This is not an integer. So this one also is not a polynomial. So the first thing we look for is to see, is it a polynomial or not? Neither one of those were polynomials. Let's try a polynomial example. So here I have f of x is equal to 108x cubed minus 39x to the 5th plus 3x to the 7th. So let's look at this one and determine the end behavior. The first thing I'm going to notice is that my degrees here are not in descending order. Let's put this polynomial first in descending order. That way we can see our leading coefficient and also that degree of my polynomial. So the 7 is the largest one. It's a minus or a negative 39x to the 5th. And then my smallest degree is that 108x cubed. That's the one with the smallest exponent on it. Now that I have it in descending order, I can notice each part. The first thing I'm going to look for is that leading coefficient. The leading coefficient is 3. What I care about that when I'm thinking about the end behavior or what my polynomial looks like is I care whether that is a positive or a negative number. Here I have a positive number. So that positivity tells me it's going to rise on the right. Then, once I know that it's going to rise on the right, I have to know what's happening on the left. And the degree of the polynomial lets me know what's happening on the left. In this case, my degree is 7. So that means because that 7 is odd, it's odd, I know I'm going to have opposite end behavior. So if it's rising over here, then on this side it must be falling because it has the opposite end behavior. So therefore it's going to fall on the left. Now that I've found what's happening on the right and the left, let's just talk about some other characteristics of this polynomial. For instance, I can tell you how many terms I expect. I expect, because the degree of the polynomial is 7, I expect there to be 6 terms. And because of the degree of the polynomial is 7, there will be 7 roots on this polynomial. So from here, we can now sketch this function. So I know that it's going to rise on the right, it's going to fall on the left, and I'm going to expect 6 turns. So 1, 2, 3, 4, 5, 6 turns. Let me count them. 1, 2, 3, 4, 5, 6. It's rising on the right and falling on the left. So I expect my graph to look something like that. Just for practice and review again, before we did f of x, f of 0, but what if I said f of x equals 0? In that case, I know that my y value is equal to 0. Let's substitute in 0 for f of x and see if we can find our x value. So I'm just going to take my f of x here and replace it with 0. And I'm going to use my descending order, 3x to the 7th minus 39x to the 5th plus 108x cubed. And I'm now going to solve for x. So here, the first thing I'm going to do, whenever our degree is, the highest degree is larger than 1, we want the other side to be equal to 0 in order to be able to solve it. And then we do our favorite thing. We're going to we're going to factor it, our favorite thing to do. So I'm going to look for my factors. Well, each one of these has an x, and in fact, they have an x cubed in each one of them. So I know I can factor out an x cubed. Then I'm going to look to see if a 3 is in each one of them. Well, I know 3 goes in there. 3 goes into 39. 1 plus 8 is 9, so yes, 3 goes into 108 too. So I'm going to factor out a 3x cubed. If I factor out a 3x cubed here, that leaves me divide 3x to the 7th power by 3x cubed, and you end up with 3x to the 4th. Notice if I multiply those, I get 3x to the 7th. I divide my 39x to the 5th by 3x cubed, and I get 3x squared. And then here I divide and I get 36 or 36. Now I'm going to use my AC method to factor in here. Remember, my A is 1, my C is 36, so my AC is 36. I'm looking at factors of 36 that multiply to be 36 but add to be a negative 13. Well, 1 and 36 don't add to be 13. 2 and 18, no. 3 and 12, no. 4 and 9, oh, together those will make 14. I need it to be a negative, so a negative times a negative will make it a positive, and a negative plus a negative will make it a negative here. Since my A is 1, I can just factor it straight to the end, so that I have 0 equals x cubed. Here I have x minus 4, or x squared, in order to get that x to the 4th power, and x squared minus 9. Oh my goodness, each one of these is a perfect square. So here I have a difference of squares. Whenever we have two terms, we look for that difference of squares. So I have 0 equals 3x cubed, x minus 2, x plus 2. That's how we factor a difference of squares. And then x minus 3 and x plus 3, because the square root of 9 is 3 and the square root of x squared is x. Notice that if I write these as linear factors, here I have it factored. I could set each one of those equal to 0, but I want to write this just to show you something as linear factors. If I did that, I would have 1, 2, 3 x's sitting there. And there I've got minus 2, plus 2, minus 3, and plus 3. By the way, I could divide both sides by 3. 0 divided by 3 gives me 0. and this side of my equation divided by 3 just leaves me with that. I now am down to my linear factors. Notice I have 1, 2, 3, 4, 5, 6, 7 linear factors, and that's what we said we were going to have when we talked about those roots. If I solve for each one of those, these x's are each 0, so I'm going to have a triple root there at 0, 0, where my x is 0 and my y is 0. I'm going to solve for my x here, and I end up with 2. So there's going to be a point on my graph at 2 where my y is 0. That 2 is going to be an x-intercept. If I solve here, x plus 2 equals 0, that gives me a negative 2, and the y is still 0. If I solve for this one, I get 3, 0. So there's a point on my graph at 3, 0. And I'm going to have a point on my graph at negative 3. If you make x plus 3 equal to 0 and solve, you get negative 3. So there's a point on my graph at negative 3, 0. This one is a triple root. It showed up 1, 2, 3 times. So 1, 2, 3, 4, 5, 6, 7 roots in that polynomial. So there's how we're going to do the degree of our polynomial, the end behavior of our polynomial. First thing you look for is your leading coefficient. What's important about that leading coefficient is whether it's negative or positive. You should tell your reader if it is negative or positive, and then what's happening on the right. Then we look at our degree of our polynomial, and what we care about that degree is it odd or is it even? You should tell your reader if it's odd or even. And then if it's odd, it does the opposite in behavior. And if it's the same, it does the same, even, it does the same in behavior. And then from that, what's happening on the left? Then the number of terms is your degree minus 1, and the number of roots is equal to the degree of the polynomial. And then you're able to sketch it based upon that. So there are some examples of finding the end behavior from your polynomials. Math Made Simple is Simpson Math. Thanks for watching.